And I would like to impress my thanks to Professor An for his kind invitation to come here. And as a matter of fact, this is my first time to South Korea. Yeah. And if you, for many years ago, 15 years ago, at that time, this year, also October, my first time to Korea, and I worked in the Research Institute of Chemical Technology for 1 year and a half. At that time, I did a research work for syngas conversion to methanol and DME in that institute with Dr. Q1 Lee and Dr. Chen K1. And we worked the structure of this very typical catalysis. Yeah, this is widely used. And my story also, today my talk also starts from the background of this story. This catalyst is widely used for methanol synthesis in industry and also for water gas shift reaction. For several decades, the people is working on optimize the performance of this catalysis, like copper sintering interaction with zinc oxide or something like that. And in the early, about 2002, some people go to more details to find that the efficiency of this catalysis is largely dependent on the nanostructure. That means very nanoscale, like 5 nanometer, this very small scale under reaction conditions or closely to the reaction conditions, some temperature and atmosphere, you can find not only the size, but also the shape of these copper particles also changing. And another question is that how about the zinc oxide? Also, they should have some response to the variation of copper particles under the reaction conditions. And this is the start of the nanocatalysis. Actually, if we go to the more details for catalysis, the reaction takes place on the surface of nanoparticles. So the shape and also the size of these particles determines their surface structure. More specifically, the coordination of the atoms on the surface. If the coordination is different, the chemical property should be larger different. That causes larger difference in the reaction performance. So at least they have two aspects to influence the surface, crystal surface, that is at least in the shape and the size of nanoparticles. And also many people have been done from the very beginning to control the size. At a very small particle size, they can also adjust the active size of the catalysis. This is a typical example from Professor Masateki Haruta from Japan. He studied the gold nanocatalysis. This is a well-known story, and the crystal size is 2 to 3 nanometer. The reason is that with decreased size, the active size is largely increased. This so-called active size actually is represented by the surface atoms. Their coordination number is much less than normal case, making them more active for the reaction. That is the intrinsic reason for decreasing the size by increasing the catalytic activities. And on the other hand, if we make the surface of the catalytic particle expose those low coordinated atoms, that means we could largely or greatly increase the active sites on the surface, the density of those active sites. That's why some people analyze the possibility by changing the shape of these particles. That means changing the shape, they can expose different crystal facets. Those facets, the coordination number of the atoms can be adjusted. If can be make them more or less coordinated, we can make them more active for the reaction process. Actually, this is already has been confirmed by some surface chemistry. For example, this is a typical old story, and also say that the surface, of course, due to the coordination of the ion atoms on the surface, not only influence the activity, but also we can detect it also influence the selectivity of the reactions. From practical reactions, They also have some good examples for metal particles, especially for noble metal particles. This is a typical example from the work for platinum nanoparticles. Even if they keep the same size, 5 nanometer, but the reaction rate is rather different because of the shape of the particle is changed at such a small nanoscale. And also for some electronic catalysis also clearly shows this size effect, this shape effect in determining the activity of the catalytic particle. And also at the same time, as I said, the shape also can change the selectivity of the space reaction. For example, this platinum cubic used for hydrogenation of benzene, and it's rather different from conversion of spherical particles in the selectivity of benzene or some other products. And even for some chiral hydrogenation reactions, the selectivity can also be adjusted by the shape of the platinum particles. In those years, this kind of work often appeared in the literature, or some journals emphasizing the shape of the metal particles and also the size of metal particles. But in catalysis, we still have another important player, that is metal oxide. For metal oxide, it's more difficult to control the size and shape because generally we should have the precursor followed by thermal calcination at high temperatures. This is different from the precious metal particles. Usually they obtain the metal particles in liquid solution with the protection of surfactant or template. That make the size and shape stable. But for oxides, we must experience high temperature treatment. And actually, the bonding is chemically rather different. So in those years, in addition to the metal particle size, we also studied some for metal oxide, controlling the shape and morphology, and to examine the catalytic performance for practical applications. So today I give you some examples to demonstrate the shape of the metal oxide do affect their catalytic performance to some extent. And also, they can adjust the metal support interaction. That means the shape of the oxide also influences its interaction with the common metal particles with respect to activity, selectivity, even for stability. Okay, we start from this typical example is cobalt oxide. This is widely used for steel oxidation reaction for many years. And usually most people use the spherical particles and decrease the size, also observe the increase of the steel conversion rate. And we change the size, the shape at this small diameter, we change the shape into nanorods, and we find the very significant change in the activity performance. So we started from the solution chemistry to control the shape of this material. If we slightly modify the conversion of precipitation method using very simple elegant ethylene glycol in the precipitation process, we can properly control the shape of the precursor cobalt hydroxide carbonate in the solution. And if we normally we get these short the precursors, so this is get the rod shape of the precursor, and we followed by thermal treatment of these two precursors to make a comparison. Normally, if we calcine the cobalt hydroxide precursor prepared by routing precipitation method, we get the cobalt oxide particle. This is very normal. And if we analyze the detailed crystal structure, we find that those particles mainly exposed to the 111 surface. This is well known for also for many decades, and the active sites often exposed as defects. That means the space, edges, or the corners. And if we start from the rod-shaped precursor followed by thermal calcination, we get this type of the cobalt oxide rods. If we also have a very detailed analysis of the crystal surface of those rod-shaped oxide, we find that It's mainly exposes the 111, of course, it should be exposed, but also on the narrow side, there has exposed the new crystal facet, that is 110 surface. And we used for CO oxidation with these two samples under the same reaction conditions. We find that their performance is largely different. The difference can be as high as 10 times. That means on the nanorods, it is very highly active, and the nanoparticles, this is the spherical particle, it's the normal performance as proposed, reported in many articles previously. And we analyze the kinetics for these particles. We find that the reaction kinetics is the same. Activation energy, also reaction order with respect to CO and oxygen, they are almost the same. The only difference is that the reaction rate, this parameter, it increases very much. That means the active site, the number of the active sites and the nanorod shape is about 10 times larger than the nanoparticles. If we perform some chemical titration analysis, we can find this correctly. And how the active number becomes so larger on the nanorod surface. And we find the coordination indicative that for this nanorod, the narrow side contains the 110 surface. So this surface is constructed by cobalt 2 plus and cobalt 3 plus. This is very important. Usually this surface cannot exposed on the surface for normal spherical particles. But in the rod shape, they have space confinement or something like that. It exposes 40% of 110 surface. So that means the cobalt 3 plus is density on the surface of this nanorod. That's why it causes the high activity than the typical spherical particles of cobalt oxide. So after this work, we also want to confirm the stability of this nanorod. We operated some other reaction at the 500 degrees C. We still confirm the stability of this nanorod and also the presence of the active site even after the reaction. Okay, so followed by this concept, we used for another metal oxide, we also get the same phenomena. That is more commonly iron oxide nanorods. So this oxide is very cheap and is also very environmentally benign materials. And we also started from the solution chemistry to control the shape of the precursor. And we get this iron hydroxide precursor followed by thermal treatment. So we get porous nanorods of iron oxide. And we can also have analysis for this side or the cross section of this nanorod. We determine the morphology like this. That means this nanorod exposes these two crystal faces and their coordination feature seems like this. So the only advantage is that as this rod shape, sometimes, usually for iron oxide, the iron is under the oxygen. But in this case, iron can be partially exposed, directly exposed to the outer surface. And then we use it for important reaction. This is also typically used for Denox process as the previous talks this afternoon. And this ammonia is also Euro is also widely used now practically for this process. And they have 3 types of catalysis at this moment. And we compared this iron oxide, so you can find the operation window for this normal material is almost overlaid with the industrial catalysis. And if we experience temperatures ups and downs, and we still find very stable performance and also stable morphology of this metal oxide, iron oxide. And we used for long-term stability test to see the possibility or the potential application of these very cheap materials. We tested for more than 100 hours with the rare Denox gas conditions. we find the sulfur oxide and also water do lower the activity, but it is only a reversible process, not the irreversible process. So after the test, at this point, we take the sample out to see the structure. It is to the where rod-shaped structure, and also the surface is also disposing the iron plus and the oxygen anions on the surface. So the performance of this iron oxide still came from the morphology effect. And because they can partially expose the iron species on the surface, it enhanced the absorption of two important reactants. One is ammonia, another is NO. If we compare with the conversion iron oxide to absorption for these two reactants was largely increased. That's why they showed very high activity for this denox process. And after this, we examined for many of other oxides, also find some similar phenomena of this kind of morphology-dependent catalysis. But there is a precondition that the diameter of the nanorod cannot be too large. If it's more than 100 nanometer or 200 nanometer, this kind of morphology-dependent phenomena becomes not so significant. Hopefully, if it's less than 10 nanometer or 5 nanometer, it's more significant in changing the catalytic performance. And with this metal oxides, we want to see how they affect the interaction of coming metal particles. So this is a typical example using ceramic oxide nanorod to support the gold nanoparticles. And we find this morphology of the support enhanced the stability of gold nanoparticles. So if we compare with conventionally, most people, ceramic supported gold is also very catalytic for a lot of reactions because of high activity for water gas-shaped CO oxidation. But this kind of interface between the series spherical particles, if exposing the 111 surface with gold, you can find the surface is not so tight. But if we change the shape of this support into rod shape, you can find the contact is becoming very tight. And the shape of gold particle is also changed. If we go to more details to see their interaction, you can find the gold atoms already deep incorporated into the lattice of ceramic dioxide. So this makes the bonding of the gold particle and the ceramic oxide support is so strong. And how strong it is, I can show you very briefly to see under very severe conditions. So this is the gold particle, this is the cereal, rod-shaped cereal support, and thereby we put this sample and in an environmental TM and heat the sample to 300 degrees C with the atmosphere of carbon oxide. And we want to see whether gold is rapidly aggregated into larger particles or it still keeps rather small particles. So in this case, from this scale, this 2 nanometer scale, you can find those particles is about 2 nanometer, 1 nanometer, even some half nanometer particles. Even though under these very severe conditions, so this is heating and also with the reduction of carbon monoxide with the substrate, you can find the vibration of the gold particles locally, and they try to leave the support to migrate and or aggregate into larger particles. But the underlying forces by the rod-shaped cereal strongly hindered their mobility. So that's why at these high temperatures you can find no small particles meet together under this condition. So this is attributed to the strong bonding from the serial support under these several conditions. And so this is for TM, you know, now the best TM can also heating the temperature to 600 degrees C, but can only introduce small amount of atmosphere, like 10 torr or something like that, because of the resolution problems. And then, so we want to conform it to the really strongly bonded gold particles. We use it for water gas shift reaction at this high temperature and for more than 100 hours. Even after reaction, at this point, you take out the sample, you find gold particles still less than 5 nanometer, still strongly bonded on the support of the support. So this is very important for the gold nanocatalysis, because from the beginning, almost 3 decades, gold is very active for a lot of reactions. But the problem is that sintering of the gold particles occurs rapidly, even for room temperature CO oxidation. So we suppose that this can change the shape of the support, can partially solve the problem with very small metal nanoparticles by strong chemical bindings. So this is the example to improve the stability of the metal particles by the shape of the support. And finally, I can give you another example that the shape of the support can also enhance the activity of the metal particles. This is the lanthanum, rod-shaped lanthanum to support the copper particles, and we use it for liquid phase reaction. So again, we start from the solution to get the lanthanum hydroxide precursor in the solution, and followed by thermal calcination of 600 degrees C to get the lanthanum oxide nanorod. The structure came like this. It's a rod-shaped structure, and the exposed crystal fuses can be determined by high-resolution TM, and we can give the illustration of the rod-type structure. It is exposed 001 and 111 surface. And these surfaces has different coordination of the lanthanum and oxygen species. Because this coordination is different, the basic is also very different from this surface to another surface. When used to load the copper particles, you can find some copper particles located on this side, and also have far less particles on this side. And we use for the liquid phase reaction, as talked by Professor Satsuma, for the alcohol to dehydrogenation or oxidation to carbonyls. And also a lot of work has been done from the group of Professor Kaneda, Osaka University, but they produce for a lot of substrate alcohols. But there only one type of alcohol is still difficult, that is primary alcohols, like octanol, butanol. This kind of the primary alcohol is rather difficult to be oxidized or dehydrogenated. And we use this process with the transfer dehydrogen. The hydrogen removed by this olefin, and we get this alcohol. Even for this reaction now, the best results yield is about 20 in the open literature. And we use this rod-shaped lanthanum to support the very good small copper particles. You can find the yield is quite promising for this process. And of course, it should be much better for other alcohols that is more easily converted. So the reason is that we change the shape of the lanthanum oxide, this support, largely contributed by this 110 surface. In this surface, you can find the coordination came like this, and the basicity of this support is much larger than the conventional lanthanum. This is the conventional lanthanum oxide. We perform the basicity. This is the medium strength basicity, not the weak. Also, we don't like to have the strong. Just this is very useful. Basic side very useful for the or alcohol activation. So you can find the shape has increased the basicity of these materials. And this basically not only participated in the reaction to activate the substrate alcohol, but also provide some space for the deployment of copper particles. And the cooperation with the copper particle and also the surface basicity comported this reaction very efficiently. That's why we get high yield of the aldehyde for the alcohol conversion process. So I can conclude like this, that nanocatalysis is still a hot topic, but many work has been done on the particle size, and I should emphasize some shape of the metal particles or the oxide particles can also address the catalytic performance significantly, but at the small nanoscale levels. And also another problem is that should be solved is those nanostructures, even the size, shape, interface. How about their variation under reaction conditions? They should be rather different from what we observed from the exist, not the under conditions. So there should have, if we can get some information under reaction conditions, that will be more useful for us to design or fabricate new efficient catalysis. And I should thank my students and also some staff in my group, and also thanks for my long-term cooperators from Japan, United States, in Germany, and China. And thank you very much for your kind attention.